Welcome to The Explainer. Today, we're going to break down one of the most fundamental concepts in all of physics and math, vectors. This is the language we use to describe motion, forces, and, well, pretty much everything about the world around us.
Okay, let's just dive right in with an idea. Imagine you're driving and you look down at your speedometer. It says 40 miles per hour. That number tells you your speed, right? It tells you how fast. But it's missing something huge. Which way are you going? North? South? That 40 mph is incomplete.
So, to get the full picture, not just how fast, but also in what direction, we need a tool that can bundle those two ideas together into one neat package. And that package is a vector. So what exactly is a vector? The easiest way to wrap your head around it is to actually compare it to what it's not, something called a scalar. Getting this difference down is the key to everything else we're going to talk about. And this right here really gets to the heart of it. A scalar is just a number. That's it. It tells you how much of something you have, its magnitude. But a vector has a purpose. It tells you how much and which way. It has both magnitude and direction. And this is where it really clicks, right? Look at these real-world examples. Could you have a temperature of 80 degrees to the east? No, of course not. That doesn't make any sense. That's how you know it's a scalar. But you can absolutely push on something with a force of 300 newtons toward the east. That's a vector. Okay, so if vectors are these powerful things, how do we actually, write them down? How do we describe them? Well, the easiest way is to just think of them as arrows. It really just boils down to these two simple ideas. The length of the arrow, that's its magnitude. So a stronger force or a higher speed would be a longer arrow. And the direction the arrow is pointing, well, that's its direction. Simple as that. But how do we describe that arrow with math? We use something called components. And you can think of components as a simple set of instructions, almost like a treasure map. Go right this many steps, then go up this many steps. Now, this is a super important distinction, so you gotta watch the notation here. Regular old parentheses, like 3, 4, mean a point, a single dot on a map. It's a location. But those angle brackets, 3, 4, that's a vector. It's not a location, it's a journey. It means move 3 units to the right and 4 units up. And if you know where an arrow starts and where it ends, finding its components is really easy. You just figure out the change in the x direction and the change in the y direction. It's always your final spot minus your initial spot for each direction. Okay, so we know what they are, we know how to write them down. Now for the fun part. Let's start doing some simple but really powerful math with them. This is a fantastic question. So we've got our instructions. Go 4 units right and 3 units up. But what if you just walked in a straight line from the start to the end? What's that direct distance? How do we find the actual length, the magnitude of the vector? Well, if you look at it, that 4 units right and 3 units up actually form the 2 legs of a right-angled triangle. And the vector itself, it's the hypotenuse, which means we can pull out a tool we all learned back in school to find its length. And there it is. The magnitude of a vector is literally just the Pythagorean theorem applied to its components. You square the x component, you square the y component, add them together, and take the square root of the whole thing. So for our vector, 4, 3, let's do the math real quick. 4 squared is 16, 3 squared is 9. Add them together, you get 25. And the square root of 25 is 5. Boom. The length of our vector, its magnitude, is 5 units. Now, this is one of the most elegant, most beautiful things about working with vectors. If you want to add 2 journeys together, you don't need any complicated geometry. You just add the horizontal parts, and then you add the vertical parts. I mean, look how straightforward this is. If vector A is 1, 2, and vector B is 3, 1, their sum is just 1 plus 3, 2 plus 1, which gives us the new vector 4, 3. It's that easy. And what if you multiply a vector by a regular number, a scalar? All you're doing is scaling it, just stretching it or shrinking it. So if we take our 4, 3 vector and multiply it by 2, we just get 8, 6. It's a new vector pointing in the exact same direction, but now it's twice as long. All right, let's get to our final concept, and honestly, this one is a real game changer. It's the idea of the unit vector. This little tool unlocks a completely new way of thinking about direction itself.
I want you to think of a unit vector as a pure directional pointer. It has stripped away all information about length or magnitude. Its length is always just 1. Its one and only job is to point and say, go this way.
And this is what makes them so incredibly powerful. It means that any vector in the universe can be described as two separate, simple things: a scalar number that tells you its length and a unit vector that tells you its pure direction. It's the ultimate separation of how much and which way.
Now, to make the system even more useful, we have a couple of standard unit vectors that we all agree on. For any flat two-dimensional space, we call them I and J, and they are the absolute fundamental building blocks for direction. So as you can see, I is just the vector for one step to the right. That's it. It's 1, 0. And J is the vector for one step up, 0, 1. With these two, we can rewrite any vector. Our old friend 4, 3 can be written as 4i plus 3j. Same journey, just a new set of instructions. So just think about that for a second. How can these two tiny, simple arrows describe everything from the push of a force to the path of a planet? Well, it's by combining them. We just take a certain amount of the I direction and add it to a certain amount of the J direction. By breaking the world down into these basic components, vectors give us a powerful, universal language to describe the entire universe. And that's why they matter.